Where were we? So, a couple classes ago, we spoke about something very important. We defined something called the derivative, which is f prime of x. What was the definition of that? Yeah?
The limit is h is approaching 0. It's f of x plus h minus f of x over h.
Very important. Limit, of course, next week on the quiz I'm going to ask you to define that, so you should know what that is. Okay? And we use that to derive is actually the verb for it, a function, f of x. So if f of x is a function, I can find its derivative, f prime, by actually computing this limit. And we actually did a few examples. And we saw a lot of important information here. For example, we saw that the derivative of a constant, we looked at the derivative of x itself using this definition. We looked at the derivative of x squared using this definition. We looked at the derivative of the square root of x using this definition. We looked at the derivative of 1 over x using this definition. And those were just things you had to memorize. What's the derivative of c, a constant?
0.
0. Derivative of any constant is 0. Derivative of x?
1.
Is 1. Derivative of x squared?
2.
Is 2x. The derivative of radical x?
1 over 2 radical
1 over 2 radical x, right? That one we had to multiply and divide by the conjugate to figure it out. This one?
Negative 1 over x squared.
Negative 1 over x squared. That one we have to multiply by the LCD, multiply and divide by the LCD to figure it out. But we figured all this out using this definition. Now if I were to ask you, what is the derivative of x cubed? You might start out the same way. You might say, well, that's going to be the limit as h approaches 0 of x plus h cubed minus x cubed over h. Now for some of you that might be a pain to actually start to compute. You have to write down x plus h 3 times in a row and start expanding parentheses. Some of you might actually know about Pascal's triangle and actually know how to get through this relatively easy. That's going to be what it is. And of course you continue. But as you can kind of see from this, x cubed is not a crazy function. It's a very nice function in general. But as you can see, can get quite annoying using the limits. Right? What if I had x to the 100? Are you going to write down 101 terms and do all this calculation? No, right? So what we're going to do today is we're going to find ways to find derivatives much more efficiently than actually going through the limit definition. So limit definition, super important. It is something you should know, not only how to state it, but how to actually use it, because I'm definitely going to ask you to use it. I already asked you in a quiz, and it's definitely going to be on test 1, where I'm going to ask you, use the limit definition to compute a derivative. But if I don't force you to use the limit definition, how do you actually get it done faster, more efficient, without all this mumbo jumbo, right? Because here, x cubed, all right, we can get through with that. X to the 100, no. X to the minus 3 over 7, no. Like, what's the conjugate of minus x to the power of minus 3 over 7, right? Like, who even knows what that is? The goal of this class is to teach you some more efficient ways to find derivatives. And that will continue into next class. And ultimately, we're going to do a bunch of examples, but for now, I'm just going to tell you a lot of different rules and ideas and techniques, give you 1 or 2 examples here and there to kind of show you what I'm talking about. But then next week, we're going to do a lot of examples, just getting used to applying these rules and techniques. So this actually leads us into chapter 3, so section 3.1. We're going to talk about the derivative formulas and properties. So we're going to figure out some nice derivative formulas and some nice properties of the derivative. Let's start with the properties. So let f of x, g of x be, we call them differentiable functions, right? So these are functions that I can actually set up this limit and actually calculate it, and it will give me a meaningful answer. I'll get a number or whatever. C is a constant. Now, here's one property. This is true for derivatives. It's called the constant factor rule. Or constant factor property. Constant factor rule or constant factor property basically says the following. If I wanted to find the derivative of a constant times a function, then that is going to be the same as the constant times the derivative of the function. In other words, I can factor constants out of derivatives. That's going to be super useful. And if you're curious as to why, it's actually not that crazy. So if you had some function p equals a constant times f of x, what would p prime look like? Well, it would be the limit as h approaches 0 of constant f of x plus h minus a constant times f of x all over h. But now that's just a limit, and a limit property is you can factor constants outside of limits. So I can move that c outside of the limit. And that limit is the definition of the derivative. That's c times f prime. So if I want to differentiate a constant times a function, essentially what I do, leave the constant alone and differentiate the function and then multiply it. So, example, if I wanted to say, what is the derivative of 7x squared? Now, notice that I already know the derivative of x squared, but what if I say 7x squared? You can use the constant factor property. What you can do is just say I can pull the 7 out in front and just find the derivative of this function. Now the derivative of x squared is 2x. The 7 stays here, and so I multiply them, 14x would be the answer. So the slope of 7x squared at any point is given by the function 14x. And I can do that with a constant factor property. I don't have to go through the whole limit definition again, because if I just multiply by a constant, I can just factor that constant out. That's the constant factor property. Here is another important property, too. It's called the sum difference rule, or the sum difference property. And it says the following. Suppose I wanted to differentiate a sum of functions, or a difference. So I either add or subtract two functions. How do I find the derivative of this new function? Well, it turns out derivatives distribute across sums. So what you would do is you would differentiate one of the functions, and then you just add it to the derivative of the other function. And that one's also not so bad to see. Why does that work? Well, if your p of x is f of x plus g of x, then if I want to find p prime, this will be the limit as h approaches 0 of f of x plus h plus g of x plus h minus parentheses f of x plus g of x all over h. I can then group the f's, f of x plus h minus f of x. Then I group the g's, g of x plus h minus g of x when I expand the parentheses. And it's all over h, so I can actually split it across the denominator. We can split up two fractions across the denominator. And that's what that's going to look like. And now you know limits actually distribute across sums. So this actually becomes the limit as h approaches 0 of f of x plus h minus f of x over h plus the limit as h approaches 0 of g of x plus h minus g of x all over h. And of course, the first one is f prime, and the second one is g prime. So you can actually prove that if I had two things added together, the derivative of the sum is the sum of the derivatives. So I don't need to go through a whole limit definition for this. Once I know the derivative of the individual functions, I automatically know the derivative of the sum of these functions. So for example, if I were to ask you, what is the derivative of x squared plus radical x? What you would do, you wouldn't have to go through a limit definition for this. You just realize, oh, this is just going to be the derivative of the x squared plus the derivative of radical x. Derivative of this, I know because Jhevon had me memorize that, that's 2x. Derivative of this, I know because Jhevon had me memorize that, that's 1 over 2 radical x. So that's going to be your answer, right? No limit definition required. You can actually combine both techniques, the constant factor rule and the sum difference rule. So if I had the limit of 5x squared minus 7 radical x plus 3 over x, and I wanted to differentiate that, I can just think of these one at a time. 5x squared minus the derivative of 7 radical x plus the derivative of 3 over x. I can, that's by the sum rule. Then I can just do the constant factor rule, take that 5 out, take the 7 out, and take the 3 out. And now I can just apply these rules. Derivative of x squared we know is 2x times the 5, that's going to be 10x. Derivative of that is 1 over 2 radical x times minus 7, that's minus 7 over 2 radical x. Derivative of 1 over x is minus 1 over x squared, so this is minus 3 over x squared. By the way, these two lines, I don't expect, you don't need to write these. Don't need to write. I'm just doing it for emphasis, just so you see how the rules are breaking down. But you can jump from this line to that line if you see how it's happening. But yeah, so you have a bunch of things added together. You can split the derivative across these things. You can factor out any constants from those things, and then just apply derivative rules for a function that you know. No limit definition required. I probably don't have to convince you how annoying it would be to actually do the limit definition on this guy. F of x plus h here, x plus h here, x plus h there, minus that whole thing. You'd have to split it up, and a part of it you use a conjugate, and a part of it you multiply and divide by the LCD, and a part of it you expand. Like it'll be a nightmare doing the limit definition for that. But we don't have to, because of these rules, the constant factor rule and the sum difference rule. Here are some other things that are going to make our lives easier. Now, the next few things I'm just going to tell you, you're going to have to take my word for it. Other useful facts. The derivative of the exponential function, e to the x. So the e to the x, very important function, y equals e to the x. How do you differentiate that function? Well, one of the things that's special about this function is that besides the function y equals 0, it is the only function that is its own derivative. Without a constant factor, you know what I mean. The derivative of e to the x is e to the x. Now, I'm not going to prove that. If you want to see the proof for that, I actually do it in my 1206 class. You can watch the 1206 lectures. But this is just something we know now. E to the x, the derivative of e to the x is e to the x. Now, really important one. There is something called the chain rule. Now, the chain rule tells us how to differentiate composite functions. So, I want to know, how would I differentiate something that looks like this? F of g of x. Right? So that's a composite function. So I have two functions, f and g. Take one function, plug it inside the other function. That new function that I just created, how do I differentiate it? How do I find the slope of the tangent line? Well, it turns out, and again, not going to prove this to you, just take my word for it. I proved it in another class, Math 201. If you're interested, you can watch that. But this is applied calc, so just take my word for it. You are going to start by differentiating the outer function. Notice that I left the inside function alone. Then I'm going to multiply by the derivative of the inside function. Okay? So that's how you want to think about this. Derivative of outer function, parenthetical statement, leave the inner function alone. Students so often forget that. They start to try to differentiate the inside right away. Don't do that. Then you multiply by the derivative of the inside, the inner function. This is called the chain rule. Very important derivative rule. It allows you to differentiate composite functions. So let me show you an example of doing that. So, suppose my f of x is the square root of x, and my g of x is x squared plus 1. Then, if I form f of g of x, that guy is going to be the square root of x squared plus 1. Right? Take this, plug inside of that. Now if someone were to ask you, what is the derivative of this new function? Right? What is that derivative? Right? So I have two separate functions. Individually I know how to find their derivatives, right? So we know the derivative of this is 1 over 2 radical x. We know the derivative of this is 2x. We know the derivative of 1 is 0 by the previous rules. So individually I know how to find their derivatives, but now I took one and I put inside the other one to form this new function. How do you differentiate that new function? Right? So clearly here there's an inner and an outer. Namely, your square root is like the outer function, right? And inside that square root, you have the x squared, which is the inner function. So the square root is outside encasing the x squared plus 1, right? So you're going to look at this and you're going to tell, hey, there's an inner and an outer function here. So how does the chain rule tell us to deal with this? Well, the chain rule says differentiate the outside function, right? How do you differentiate the radical sum of something? Well, it's 1 over 2 times the radical of the thing, right? And at first, you leave the thing alone. Don't do anything with it. X squared plus 1, right? Because I know the derivative of this, f prime, is 1 over 2 radical x. So if I just differentiate the outside and leaving the inside alone, it'll look like 1 over 2 radical of the thing, right? So that's this first part here. And then, what I'm going to do afterwards is I'm going to multiply by something. Multiply by what? Well, the derivative of the inside function, right? So this here is your g of x. I want to multiply by g prime. What is g prime? Well, it's a sum of two things, and we have the sum difference rule. So I just differentiate each of these things individually and add them together. Derivative of x squared is 2x. Plus the derivative of 1 is 0. So this becomes 2x over 2 square root of x squared plus 1. The 2's would cancel. So this derivative is x over the square root of x squared plus 1. And I'd figure that out using the chain. Yes?
Would you always be given like what each individual function is?
No, the problem's gonna show up like this. Yeah, I do this for emphasis so you can see this function could be constructed in this way. Do that. Be sure to try it, so if you don't know how to do it, you can ask me a question about it. You won't know unless you try. Try to apply the chain rule, even though there are other ways to do this problem. Try to apply the chain rule specifically. It is? What do you get?
I said the derivative of the outer function was 2x.
Right, so how do you write that down?
So I did
2?
2x times, then like the derivative of the inner function, which is 1 over 2 radical x minus 1 over x squared.
Nope, something's off. Yeah,
The first part should be 2, and then in parentheses, square root
right.
of x.
You have to leave the inner function alone first, the g of x. So, yes, if you have something squared, the derivative is 2 times that thing, but you have to leave that thing. So the derivative of the outer, if I just think of this as something squared, the 2 comes down, it's 2 times that thing to the 1 power, right? Because the derivative of x squared is 2x to the 1 power. So now you multiply after that by the derivative of the inside. So that's what the answer would look like. So it's going to be 2 times this times that. What would the derivative of this look like? Who's your inner function in this case?
E.
E is the inner function. What is that plugged into? What would E be plugged into here? Yeah?
The g of x is plugged into e. So e
The
is
g of x
outer
is plugged into
function.
e to the x, right? You can kind of see that if my f of x was e to the x, and I just had this function g of x, and I put it inside of that, I would get this, right? So my f of g of x would be e to the g of x, right? So the g of x is my inside function here. Okay. Now that I've identified who's my inner function, I had an exponential function and I plugged something into the power. How do I differentiate it? What was the derivative of e to the x?
E to the x.
Right, it didn't actually change. So the derivative of the outer function is to not do anything. Of course, you leave the inside function alone. Then what are you supposed to do?
Times g prime of that.
Times g prime. You multiply by the inner function. So, in other words, if I wanted to differentiate e to the g of x, that's just going to be g prime of x times e to the g of x. Or, a little bit more concisely, the rule is usually stated in terms of some variable u. So if I had to differentiate e to the u, where u is some random function, the derivative is going to be u prime times e to the u. So the derivative of exponential, the e with base e, is the derivative of the power times the original function. So for example, I could say, what is the derivative of e to the x squared? What is the derivative of e to the x squared? Yeah.
2x times e to the x squared.
Right. Want to differentiate e to something, it's the derivative of the power times the original function. We know that by the chain rule. Don't have to go through a limit definition. Another important thing to know how to differentiate is the logarithm. So, I would ask you, what is the derivative of ln of x? What is that? Okay. So, turns out that we can actually figure this out. So if I set y equals ln x, notice that we want y prime, right? The derivative of y. What is the derivative of that function? Now, I haven't given you any rules for the log function, so the log is a problem. And what do we do when a logarithm is a problem? You exponentiate. You exponentiate to get rid of logs. So what I would do is exponentiate both sides, e both sides. On this side that cancels, and on that side I get e. Now what I'm going to do is differentiate both sides. These two functions are the same, so their derivatives are going to be the same. So, what is the derivative of e to the y? Yeah.
Y prime times e to the y.
Y prime times e to the y. How do we know? This rule is how we know. Derivative of anything is the derivative of the power times the original. Derivative of e to the y is the derivative of y times the original. Derivative of x, we derived that last time, that is 1. Now since I want y prime, I can solve for it. So y prime is going to be 1 divided by e to the y. But what is e to the y? Well, e to the y is x. So that's 1 over x. And so that leads to another rule. How do you differentiate the natural log? Well, the derivative of ln x is 1 over x. And that's just that's a rule we know now. Now, of course, every time you remember a rule, you can make the rule more general using the chain rule. You'll notice that this makes the rule that I gave you before, the derivative of e to the x is e to the x, it makes it more general. It in fact includes that example, because if my u is x, my u prime is going to be 1, and I'll end up with the derivative of e to the x is e to the x anyway. So this is even more general than the first rule I gave you, and so this is a very specific rule, but we can actually make that more general by the chain rule. What would the derivative of ln of some random function be? Well, it's going to be the derivative of the outer function, which is just 1 over the thing, multiplied by the derivative of the inner function. The inside function is u, so that's u prime. So in other words, the derivative of ln of some function is u prime over u. And if you're going to memorize only one of these two formulas, memorizing the chain rule version is the better version to memorize, right? Because it includes this version, right? If your u is x, u prime is going to be 1. So this is the chain rule version. The derivative of log of something is the derivative of that thing over the thing itself. What's that derivative? Yeah.
So would it be 2x plus 1 over x squared?
Minus 1 over x
Or
squared?
minus 1 over x squared, and then just over x squared plus 1 over x plus 1.
Exactly. You take the thing, put it in the denominator, on top, put the derivative of the thing. That's how you differentiate a log, natural log or something. That would be the answer. Right? No limit definition required. Now, to start off the class, I used x cubed as an example. Hey, it'll be pretty annoying to find the derivative of x cubed using the limit definition. Let's do even better. Let's go more general. Now, we're going to look at how would you find the derivative of some power of x, like in general, right? So yeah, x cubed is going to be annoying. What if it's x to the 1,000? Even more annoying. It's probably going to be nice to find that derivative. This is, terms in a polynomial looks like this. Polynomials are functions we use all the time. We're going to want to know how to deal with them. How would you find the derivative of x to some power? Right? Here, n is a constant. That's going to be important. How do you do that? We're going to kind of play the same game over here, actually. So set my y equals x to the n. We want y prime. I want to know what is the derivative of this function. Y equals x to the n. What is y prime? So we don't know how to deal with the power, especially if the power is big or just really complicated. Maybe it has some radicals in it or something. So whenever we have a power that we don't want to deal with, what do? Log it, of course. Exponentials gets rid of logs, logs gets rid of exponentials. So what I would do is I would ln both sides. That's going to allow me to take this and move it down. And now I'm going to differentiate both sides. What's the derivative of ln y?
Over y.
Y prime over y. How do we know? That rule. Derivative of n times ln x. N is a constant. Therefore, the constant factor rule says, leave the constant alone, differentiate the function. 1 over x, that rule. So now if I want y prime, I'll just solve for it. That's n times 1 over x times y. That's what my derivative is going to look like. What is y? Well, y is x to the n. So now I have n times x to the n over x. Well, now we know by the laws of exponents, you just subtract the powers. This is going to be n x to the n minus 1. Therefore, we've just figured out how to differentiate x to some power. What is the derivative of x to the n? It is n x to the n minus 1. That's a new rule that we have now. And it's a very important rule. In fact, this has a name. We call it the power rule. Yes?
Why do we, so like for ln of y, why is it y prime over y when, and that definition just 1 over x? Like isn't it, like, does it matter?
Yes, it matters. So
Variable.
x there is just x. X is the independent variable. It is the same guy as this. Over here, when I have u and x can be different things, is the point. So this doesn't have to be x, it could be some random function. Namely, in this situation, that's my u. So it's not just x, it's some other function, right? So it's telling you if you don't have just x, how do you do it? Well, you would take the derivative of that thing and put it over this. And this, the same idea actually applies here. The derivative of x is 1. Right? So you put the derivative of this thing over the thing itself. And this is just a generalized way to write that. So in general, this is going to be true. It's even true in that case, but this is more general. Your u doesn't have to be x, it can be anything. So in this case, I had ln of y. What is the function y? Well, it's x to the n. It's not x, so I can't apply that rule over there. I have to apply this rule over here, which is why I get the y prime of y. But ultimately, this is the thing you're going to want to remember. It's called the power rule. It's very important. In fact, let's use the power rule to find what is the derivative of x cubed without the need for a limit definition. Yeah,
3x squared.
3x squared. Right? You take the power, move it down in front, and then subtract 1 from the power. In fact, what we're going to do now is we're going to rederive some rules. It turns out that all these rules that I told you that we painstakingly derived a couple classes ago, you can actually get to them pretty quickly using the power rule. So, we all know that the derivative of a constant is 0. Right? It turns out you can look at that in terms of the power rule as well. Because a constant is just a constant times x to the 0, because x to the 0 is 1. Constant factor rule, factor that out. That's c times 0 x to the minus 1, subtracting 1 from the power. But ultimately you have a 0 here being multiplied, so you get 0. 0 constant is 0. What is the derivative of x? Well, we know it's 1, but the reason is that's because we can think of it as x to the 1 power. Applying the power rule, take the 1, move it down in front, subtract 1 from the power. You get 1 x to the 0, but x to the 0 is 1. So that rule makes sense again. What if the derivative of x squared? Well, applying the power rule, you take the 2, you move it down in front, you subtract 1 from the power. So that's 2x, exactly what we had before. What is the derivative of the square root of x? Well, I could actually think of the square root of x as x to the 1/2. Bring the half down in front, subtract 1 from the power. 1/2 minus 1 is actually minus a half. This means I can move that x to the half in the denominator, and that gives me 1/2 radical x. So we have that rule. If we look at the derivative of 1/x, I could actually write this as the derivative of x to the minus 1. Bring the minus 1 down in front, subtract 1 from the power, I get minus x to the minus 2. That gives me my minus 1/x squared. Right? Like I can get through all these rules that we have to use the limit definition for very quickly with the power rule, right? So. It took a long time to derive all these last time. We did all of them in like under a minute using the power rule. It's a very important rule. Very powerful as well. Pardon the pun. Here's an example for you guys to try. What is the derivative of 3x to the 5th minus 4 over x plus 2 over the cube root of x? Try to do that. No limit definition. which in general you don't have to write that out, but yes, if it helps you visualize it, then yes, separate them. And what do you do now?
And then, you could take out, you could do the constant, factor thing, so you could take out the 3
Mhm.
and the 4 and the 2. And then, since for the last one, it's 1 over the cube root of x, you could change that to a fraction, which is 1 over x to the 1/3, and you could bring it up to the, numerator, so it'll be 1.
So it would be x to
to
the
the negative 1 over
negative 1 over 3.
And then you find the derivative of all of them.
Okay.
It'll be
So start out, what is this? Derivative of this?
15x to the 4th.
Right, so it's 5x to the 4th times this 3, so that's 15x to the 4th.
Plus 4 f over x squared.
Right, so we know the derivative of that is 1 over x squared. You could have also written this as x to the minus 1 and do the power rule. You'd get to the same place. This one,
Minus 2 over 3.
so it's minus because of this minus here. The minus 1/3 comes down, that's 2/3 x
X
to,
to the 2/3. X to the 2/3.
no, what's the rule? You have to subtract one, right?
Oh, not the one.
You have minus 1/3 minus 1, what is that?
Negative 4 over 3, so.
Minus 4 over 3, right? You just think of the 1 as 3 over 3. So it's minus 1 over 3 minus 3 over 3, you get minus 4 over 3. Yeah, that's it. Yeah, like I said, in general, you don't really have to write down these 2 lines, but it helps you to visualize it, write it down. Don't try to do things in your head that you're not ready for and then you get it wrong. So, yeah, that would be the derivative of that. Which, again, would be very annoying using the limit definition there. But with the power rule and the constant factor rule and the sum difference rule, it wasn't that bad. So for this section, we have like 20 examples I want to get through, but I'll give you guys the first 7 to think about over the weekend, because our quiz next week is going to involve stuff like that. And just so you're also prepared for the bonus, be warned here that to do some of these will require using rules that I haven't told you about. But if you can figure out what those rules are and look it up, you might get the bonus bonus. So, find the derivative of the following. The first one, y equals x cubed e to the x. Y equals the square root of x e to the x. Y equals 3x squared ln x. Y equals x times square root of x. Y equals x plus 1 over x plus 2. Y equals x squared over 2. Y equals 3 over the square root of x. So it turns out 3 of those, I'm not going to tell you which 3, we could actually, based on what I taught you today, you'd be able to do. The other 4, you can kind of think of that as a bonus. If you figure out how to do the other 4, and you'll figure out what rules would apply to them. That'll be good prep for the quiz. The quiz next week covers everything we did this week, including up to knowing the power rule, how to differentiate exponentials and logarithms. Stop there. We'll do these examples and more next time.